Good morning, ladies and gentlemen. We will start our plenary talk today. The presenter will be Professor SAMI Kam. I will make a brief presentation. Dr. SAMI Kam is an assistant professor in School of Sustainable Energy Engineering at Simon Fraser University at Canada, SFU. He obtained his PhD in mechanical engineering from MIT in 2020. At SFU, Dr. Kam leads the engineering interface for sustainable energy group, which aims to improve the performance and longevity of sustainable energy systems by fundamentally understanding and tuning electrochemical-physical interactions at interfaces, with a particular focus on enhancing CO2 capture and conversion processes. He has raised over 1.1 million Canadian dollars in research funding. He previously worked in the rare earth mining industry in Canada and was a science and technology advisor to the chief scientist of Natural Resources Canada. He is the recipient of many awards, including the Action Canada Fellowship from the Government of Canada in 2021, and the Marcel Pourbaix Awards for Best Poster in Corrosion Science received at NACE, International Corrosion Conference in 2019. Please, Professor SAMI.
Thank you so much for the kind introduction and for the invitation to be here, Dr. Edson and Dr. Fernando. I don't know where they are, but thank you so much. It's my first time here in Brazil, very excited to be here. So as Dr. Edson mentioned, I'm coming all the way from very cold Canada, so extra happy to be here right now. But yeah, I'll be presenting my group's research on interfaces and walking you through a journey of how some of these fascinating interfacial interactions can be used to modulate efficiency in sustainable energy systems. So picture this. This here is the sustainable energy landscape. It's kind of like the dream we all have, right? Eventually, no fossil fuels, all of these different systems, they're powering our clean economy. But as you see, a lot of these, you cannot only have one thing at a time. You can't have only solar, you can't have only wind, you need everything, right? And this is an engineering conference, right? As engineers, what you all like to do is think about performance, longevity. So performance, you're asking questions like, how efficient is this conversion process? And in longevity, you're asking questions like, well, how far can this take me, right? If I have something out like there in the ocean, then is it gonna serve for 20, 30, even maybe 50 years, right? So that's the fundamental focus of my research group. It's that we feel that a lot of the challenges in these systems, they happen at interfaces, which are boundaries between materials. And just before I start presentations, I like to do like a theory so we're all on the same page, right? So bear with me as I go through this. What exactly is an interface? What exactly is a surface? So first of all, a bulk phase, right, is matter in 3D space. So right now, the atmosphere around us, you can think of that as bulk phase. An interface is defined as a boundary between two and more materials. But specifically, a surface, it's a type of an interface where you have a solid gas or liquid gas boundary. So as an example in this photo here, right, this is in Vancouver. And my definition of a beach has changed since I've been in Brazil, so that's why I call that. Doesn't compare to what we have, what the beautiful beaches you have here. So some interfaces you see there's a solid liquid interface, which is the oil tanker with the ocean, and many more interfaces there. Can we have a gas-gas interface? That's a question for you all to think. If you think there is, catch me after my presentation. So interfacial science and engineering are two distinct concepts. And I like to call this, quote this from Dr. Wolfgang Pauli. So as you're noticing, the Nobel Prizes are being announced, right, this week. So Wolfgang Pauli won the Nobel Prize for physics. But in his lecture, he said this thing very interesting, right? God made the bulk, but devil made the interface. So we like to call it's another exclusion principle from him. So the way it manifests itself in science for interfaces is the boundary between materials, right? So if you're a green molecule here inside, you're happy because you're surrounded by your own friends. But if you're up there at the interface, like that unhappy molecule there, then there's some different intermolecular forces of attraction compared to the bulk. So just by that definition, the interface is where a lot of challenges happen, right? And if you think about it, this little boundary here, right? This boundary is less than 1% of the overall material, right? But it can be really, really, unfortunately, bad in terms of challenges. So that's where engineers come. You start asking questions, well, what can we do to make that unhappy molecule happy? So a couple of things you can do is to replace it with some sort of an intermediate red layer where you now have this sort of bond between the two phases. Or you can also make hills and valleys. So that same material there, if you make it like that, then you're changing the morphology. So really, these two options are exhaustively the only options you can do with an interface. Either change the chemistry or change the morphology. So let's keep that in mind as I go through my talk. A couple more theory concepts, and then I'll dive into the research, I promise. So the first thing is hydrophobic materials and hydrophilic. So again, looking at surface chemistry as one lever, you can have two types of surfaces, a hydrophilic surface or a hydrophobic surface, and that's defined by the contact angle. So if the contact angle is less than 90, it's hydrophilic. If it's greater than 90, and a good example is a non-stick pan. In a non-stick pan, coating like the red coating, it makes a hydrophilic material like steel hydrophobic, right? But now this is where texture comes in. Remember the hills and valleys that I said? So if you take that smooth material and now add these hills and valleys or microtexture it, then the contact angle becomes 0. That means you can get extra wettability. And then the same thing with hydrophobicity. If you make it textured, you make it extra hydrophobic, right? So the way surface scientists, we do this is contact angle measurements. So again, a hydrophilic surface, contact angle is less than 90. But now if you texture it, it becomes extremely super hydrophilic. That means the contact angle, as you can see in that video, is 0. A hydrophobic surface is 90 degrees, but then if you add texture, you make it extra hydrophobic. So that means now you have this contact angle that's greater than 150. The droplet doesn't want to interact with the surface. Again, as we think in our group, right, is how do we engineer beyond what we know with these surfaces? So one category of surfaces that have come up in recent years are called lubricant-infused surfaces. And I refer you to these papers for more details. But really, what I showed earlier was a hydrophobic surface. The idea here is now, well, if you coat it with a liquid, and the liquid is shown in yellow, then that liquid, if it is water, it's repelling to water, then you get an extra slippery surface. So this, again, it's inspired by nature. I think that video is not playing, but it's really a droplet of water sliding down. So that's what a pitcher plant does. It's able to, when an insect lands on it, it sees a slippery surface, so it can, essentially, it slides down. One common everyday example is if you've tried cleaning a Teflon-coated pan, you know it's really hard, right? Because you always have a thick layer of oil. Or even if it's not visible to your eye, if you take it in the microscope, you'll see that there's a thin layer of oil always on your Teflon pans. So I really recommend everyone throw out your non-stick cookware. It's not good, actually. All this stuff is accumulating over time, and it's becoming worse. Good old school steel, iron. You're going to get more sticking, but that's okay, right? It's more crisper. So it's very apt because I was looking at the meaning of the city of Belo Horizonte. It means something like beautiful horizons. So I put a little bit of the horizon context in here as well. So what we're interested in my group is, well, how do we bend the horizon or look at new directions in the research? So this is where lubricant-infused surfaces come in, and I'll talk about that in my work shortly. But we're also looking at some more horizons, and these ones, I'm going to keep it as a surprise. We'll look at that towards the end. But essentially, that gives a structure for my research side of the presentation. This is all the theory, right? The research side will be covering these 3 topics. Okay, so back to the sustainable energy system. The first part I will talk about is how do we use these lubricant-infused surfaces to enhance the longevity of hydrogen infrastructure. So hydrogen is quite big in Canada. I believe also it's growing. The momentum is also growing here in Brazil. But the idea is that when you burn hydrogen, you only get water. It's clean, but it's also, you can transport that instead of natural gas. So different levels of government in Canada start to make these different hydrogen strategies. But in a lot of ways, if you look at the wording of these documents, it always says you need to deliver hydrogen safely and reliably, right? So then that begs the question, how safe is hydrogen, right? I think we all learn in textbooks that, yeah, if you burn hydrogen, it's very clean, you get water, like I said, but is it actually really safe? So I did this very quick proof of concept experiments with my students, right? So when you get a steel wire, if you try to bend and deform it, it doesn't break, and that makes sense because steel has a fairly decent elasticity, right? Now, if you place that same steel wire in hydrochloric acid and let it sit there for 15 minutes, and as you saw in that video, right, there are bubbles evolving because hydrochloric acid is corrosive, right? So then when you put that same wire and then you do the same thing, you'll see that it breaks, right? And nothing else was done. It was the same wire, you put it in acid for 15 minutes, it's lost its strength. So, you know, if you're thinking what's going on, it's probably corrosion, it's eating up the metal. That's true, but then this interesting thing happens, right? If you take the hydrochloric acid and then let it sit outside for 15 minutes, the wire, and then you do that test again, you see that it's not breaking. In this video here, it broke in just 2 seconds. Here, it's not breaking. That means it's regained its strength, right? So that means if it was corrosion, this wouldn't happen because corrosion is permanent. So, so again, just to summarize the observation, the first video doesn't fracture, the second one fractures right away, the third one takes many attempts to fracture. So what this is called is hydrogen embrittlement. If some of you have heard of it, you'll see some topics here that may be relevant to what you worked on. But if you haven't, please pay close attention because this is a big safety hazard that affects hydrogen systems. So how exactly does hydrogen embrittlement occur? Well, hydrogen, it's atomic number 1, very tiny molecule. So when it meets steel, it can dissociate into atoms. And then when it dissociates into atoms, it can enter the steel because hydrogen atom is tiny, right? It's just, it's got that 1 electron and then 1 proton. So once it goes in, the steel becomes very unpredictable. It's like gaps have come into the steel, and then you can have the steel break this way. So if this doesn't scare you now, know that this is a problem because as we're developing hydrogen infrastructure around the world, storage tanks, pipelines, fueling stations, you don't want this kind of thing to happen. You want to deliver hydrogen safely to all citizens, right? So this is where some of the research, this was also the research I did in grad school combined with my first year in my faculty career, was that, well, what can we do about this, right? If hydrogen is now entering into the metal, the natural thing as engineers we think of is how can we stop that, right? So here the hypothesis was what if we used a coating, right? And that coating is essentially what we will call a barrier coating. But here in this research, what I looked at was not just any coating, but a liquid coating, right? And this is where the lubricant-infused surfaces come in. So the specific lubricant we worked with is called Krytox. So Krytox is a fluorinated lubricant that is used as vacuum grease oil here. And to show how effective it is, there are these 3 videos. So in the first one, you have a hydrogel. As soon as you put it in water, it swells to many times its own volume. In the second video, that hydrogel is coated with a hydrophobic layer. The hydrophobic layer is Teflon. And you would expect that it would survive in the water, but it's also increasing, right? And a good example of that is your cooking pan. If you have a Teflon layer, and if it has a crack or if it has a scratch, then the cooking pan is not going to work, right? So solid coatings have that issue. in the third video, which I promise you is running, there's nothing happening, right? The Krytox layer, which we call KL, that barrier layer, it's stopping the corrosive liquid from going inside. So really that video was to show you that these liquid layers, right, and these liquid layers can be as thin as 60 nanometers. It's a thin layer of oil. We showed through rigorous electrochemical experiments that it can slash the hydrogen diffusivity by almost an order of magnitude. And the important thing is that this is working not just by itself, but it's working along with this intermediate red hydrophobic layer. But just that red layer, hydrophobic layer by itself is not enough to do the job. Adding that lubricant makes the job even better, right? So I don't have time to go into details here. Feel free to refer to our publication here. But in a nutshell, what we showed here is that if you have a thin lubricant layer, then you can stop this hydrogen diffusion, which then has a lot of implications for pipelines, for storage tanks, so that way you can protect these systems, right? So this was the first part of my talk. And since this is a chemical engineering conference, and I'm actually a chemical engineer by background, I did that in my undergraduate degree. So my advice for chemical engineers is, as you're designing these next generation pipelines, all the fluid mechanics, transport, amazing, but don't ignore the interface, right? Because that's where, if you think about it, that kind of embrittlement, if something breaks, then hydrogen leaks out, you've got all these different explosion risks to conversion. So one of the papers which I had in the QR code, we looked at, once you capture the CO2, can you instantly convert it to ethanol, actually? So what we found is that because there's more mass transfer and it's rapidly coming in, you can then make that reaction faster, too. So that's one. The second thing, actually, one of my students now is working on is precipitating it as a carbonate. So that one is kind of like what shellfish do. It takes the CO2 and then converts it. My group, and personally me as well, we don't believe in underground storage. I think if you hear about that, happy to have a debate, but sending CO2 all the way down, why spend all of that? It's better to convert. So yeah, so definitely the storage, or so definitely the conversion part is a research interest.
Well, thank you very much again, Professor Sami. Just to make clear again, CAPES have a program that will be ended 30 October for partnerships between Brazilian and Canadian institutions. It's we have not too much time to write the projects, but it's an opportunity to visit SFU in Canada and to meet your program and other programs. Okay? Thank you again, Professor Sami.
Yeah. Thank you all. Yeah. Oh,
one more question.
The sandblasting of the glass, how did you do it originally?
How did
you do it originally?
Good question. So sandblasting is you've got a high pressure air, you put it in like an aquarium that has sand, and then what Oz did was he used like a parallel blasting technique, because if you do it this way, the glass breaks. But really it was very random, right? So it was essentially using abrasion. The other thing you can do is use sandpaper and make it rougher. But it turns out as long as the sand is very small, right, it's able to create microtextures. So, sorry, so the slides that just came back. So, yeah, so again, I really want to thank all the students I've had an opportunity to work with. And then I would be in trouble if I didn't acknowledge my sponsors, so all of these wonderful sponsors. I'm also recruiting PhD and master's student in my group. We have projects in all of these topics, but we also just got funding for lithium recovery from brines. So if this is of interest, please reach out.
future thing will be a nice thing to look at for future trials and future modifications in the product.
Yeah,
Thank you.
it's like a good hypothesis and stuff like that.
I don't know if it would affect the capability of the panels to
That's really
capture energy.
yeah, because it affects the transparency. So that's
Yeah.
the whole thing. We introduce something, we may make another problem worse.
Yeah.
So
But I had never known about the hydrogen, how do you say it?
embrittlement.
Embrittlement.
Yeah, I can't know your family
It's, I had never thought about because it's kind of obvious that the hydrogen is so small it's going to be through everything, but I never thought about it going through metal and damaging the whole system. It's a very nice thought and very intelligent.
And it's something that researchers, engineers, policymakers, everyone is people's safety. It's like we don't want another climate change.
Yeah, we have a teacher that says that every time an engineer solves a problem, it creates 10 more. So we are trying to make our best, but at some point we'll have to deal with the impacts of what we're doing now to try and avoid the impacts we already did.
Yes, absolutely. And it's a methodology of this kind. It's the best you can do.